All right. So Marsh really teed it up nicely in terms of talking about the importance of the prior. And so I'm going to continue on that topic, to talk about something called prior building. You know, I was talking with Nate this morning, and he was talking about how when we use deterministic problems, we can use prior information equations to bring in soft knowledge about conductivities and storages and relationships. But like with everything in the ensemble space, this becomes more difficult. And so this is one technique that Briak and I have been working on to start to bring in imprecise data with our imperfect models and use that to reduce predictive uncertainty. So what kind of data do we really have when we're building in history matching and data assimilating? Well, we have state measurements. We're all really obsessed with these, as I'm sure we are aware, right? Groundwater levels, we have to fit those really well. But to use the information in groundwater levels, we have to solve the inverse problem. We have to run the model forward, get the simulated outputs, compare that to the data, do all this rigmarole. There's a whole other type of data that we could learn from. The things that tell us directly about the model inputs. And we use parameters as a construct to represent model inputs. To use this information, we don't have to solve the inverse problem. We don't have to run the model to use this information. Both of these types of data provide learning about the parameters, and in as much as the parameters influence the forecasts, using this data also reduces forecast uncertainty. But there's a problem. The problem is our industry largely ignores this second type of data, right? Here we see a groundwater modeler from Texas telling us about his residual statistics for groundwater levels, but we're abusing or ignoring this entire other class of data. But in the Bayesian context, the prior and the likelihood are co-equal partners. Anything we can do to learn about this term, about the prior, ultimately results in a reduction in posterior uncertainty, reduced forecast uncertainty. So, prior building is about using all the relevant information we have about the parameters, but using it appropriately. So this is a busy slide, I apologize for that, but I'm trying to make a point that there is a lot of information available in most cases to tell us directly about the parameters themselves. Aquifer performance tests, multi-day, multi-well aquifer performance tests, those are sort of the gold standard. We go down to step drawdown tests, slug tests, Packer tests. I'm sure some of you are nervous that I'm even mentioning these data exist. Geophysics, we have borehole logging, surface geophysics, SkyTem. SkyTem is going to solve all of our problems, if only we knew how to use it. We have core data, sand clay fractions, permeameter tests, lithologic descriptions. Conceptual models are chocked full of little bits of information. On average, this condition holds. In general, this is greater than that. It's qualitative, it's imprecise, but there's information there. And then we get down to the anecdotal things. When we sample this well, it takes weeks to recover. There's something there about the parameters for that, about the conditions of the aquifer at that location. All of this data is imprecise in and of itself, and there's a support volume problem. How does this data relate from the core scale up to the model grid scale, right? There's the same size mismatch we deal with in a lot of cases. So the question then is, how do we use this imprecise information with an imperfect model appropriately? Well, I generally see two end members. There's the overly conservative group, I'm largely in this case, where we simply ignore these data, or if somebody calls us out on it, we average it and tell them we use the data, right? On the other side, though, there's the overly aggressive types, the Zap Brannigans of the world, who are going to force the model to reproduce those data exactly where they occurred, right? I did a slug test in this model cell, and this model cell is going to be 13.1 meters per day, and you're not going to tell me anything else about it. That's not quite right either. And in fact, there's a bias variance trade-off here. If we ignore the data, we're willing to accept higher variance when we finish in our parameters and ultimately our forecasts. If we force the model to respect these data inappropriately, we're risking bias. And as John would say, we're somewhere between useless and wrong, right? So we want to find our spot between useless and wrong. Well, what's between useless and wrong? Data assimilation, right? Data assimilation gives us the tools to use imprecise data appropriately. And nowhere in the word assimilate is groundwater levels. Assimilate is just about absorbing information into the system. And we like ensemble methods for data assimilation because they're very flexible and very efficient and very general. They give us complete control over how we define the dimensions of the problem. We can use any parameterization scheme we want, any combination of parameter schemes we want. any type of observation, any quantity we want to assimilate. And for today's purposes, what we're really interested in is the noise representation. Ensemble methods give us a lot of control over how we represent the noise or the imprecision of the information we want to assimilate. Let's see, will it go forward? Uh-oh, there it goes. Okay, I want to pause here and also say I have the very distinct honor of getting to show you the first equation of the conference. Let's get a round of applause. Okay, this is everybody's favorite equation. This is the ensemble form of regularized Gauss-Levenberg-Marquardt. It's what's at the core of IES. But in this form of it, this DOBS, the far term on the right-hand side, does not have groundwater levels or surface water flows. It has our imprecise parameter estimates. Hydraulic conductivity in this model cell was measured to be this. Storage was this. This zone of hydraulic conductivity should be less than this zone of hydraulic conductivity. Those are our imprecise data, which means since our imprecise data don't come from model outputs, we don't actually have to run the model to apply this equation. In the PEST world, we simply fill our template files, run any preprocessors that interpolate pilot points to the grid, do any sort of post-processing on the input files to summarize hydraulic conductivity statistics, and we quit. There's no model run process here. We're just filling templates, reading with instructions. So it goes really quickly, regardless of how big your model is. So we're using IES and we're using the PEST interface, but we're not actually running ModFlow for this process. But what's most important, what I like the most about this is how we represent that information content, that imprecision. So for the most precise types of data, we have our Gaussian noise, the same as it ever was, right? We put a weight on this thing and it describes how much confidence we have in the measurement. But then if we step down to the next level of quality, we can use something borrowed from the optimization world, which is a double-sided inequality. So we can say, as long as the value is greater than this, and long as the value is less than this, I'm happy with any number in that range. So I've been told storage, when it comes from an aquifer performance test, is dubious. So rather than saying I want storage to be this and it's this uncertain, I can say I want storage to be somewhere in the range of where that value was estimated to be. So it puts a lot less pressure on the algorithm to match that storage number. And then for the really lowest quality data, we can use this one-sided inequality. So if I had an observation well, and it takes weeks to recover, I would say I want hydraulic conductivity in this cell to be less than 0.1 meters per day. Right? I don't know how low it is, but I know it has to be less than some number. There's a piece of information included in that. And this is a way to specify that piece of information without forcing the algorithm to do something really precise. Now this sounds like a Rube Goldberg machine. I'm sure you're thinking I have some slug tests. I just want to use them in my model. Why do I need all this complexity? Well, it's because the model is imperfect and the data are imprecise, and we have to be clever and smart about how we use and access the information in those data. Okay, example problem. Of course, it has to be the Freiberg model. I'm obsessed with this really simple test model. And in this case, this Freiberg model has 3 layers, and we're concerned with hydraulic conductivity and storage in layers 1 and 3. And so let's assume we've done some aquifer performance testing in layers 1 and 3, and that's where we have these red dots for conductivity and these pluses for storages. So where we have those red dots, let's assume we have hydraulic conductivity estimates of varying quality. And where we have these crosses, let's assume we're going to use double-sided inequalities for storage. We're going to say I want storage to be within 1 order of magnitude of what was measured from this performance test. And then let's augment that with a little bit of soft knowledge. Where we have these minus signs, that's where we have high capacity production wells. Let's say hydraulic conductivity has to be at least 30 meters per day, or someone wouldn't have put a well there. So we're not going to run ModFlow. We're just going to do this sort of assimilation routine that goes really quickly. And we're going to assimilate, we're going to assimilate that information into a multi-scale parameterization. You can use any parameterization scheme you want. I like this multi-scale parameterization. And so what we're going to have is for every property, conductivity and storage, layer 1 and layer 3, there's 3 sets of parameters that will apply to that property. So for each one of those properties, we have a grid scale set of parameters. Those are cell by cell, geostatistically varying. We're going to combine those with a set of pilot points, which are broader scale heterogeneity, to represent broader scale heterogeneity, also geostatistical. And we're going to combine that with a layer constant to represent the mean of the field. So at runtime, when we run this thing, we're going to fill these 3 arrays, multiply them together, and then get this last array on the right-hand side. And that last array is what we're going to extract numbers from to have our observations in the PEST interface. So we're not actually going to run ModFlow. We're just going to do all the pre and post processors from ModFlow and quit. And so what does this look like? So this is one realization for layer 3 hydraulic conductivity. The first plot on the left, that's the prior realization. It does not respect any of the conductivity estimates. The plot on the right respects these conductivity estimates. So what's really cool about this, I think, is we don't have point estimation. We don't have a little blue dot with yellow around it or a yellow dot with blue around it. Because the prior realizations have a nice geostatistical character, this location needed to be lower. We didn't just drag down this point, we've dragged down a region around it that respects the geostatistical features of the prior realizations. And that's because these prior ensemble was encoded with some covariance rules, and those covariance rules have been transferred into the upgraded realizations. And so these realizations, they have not been run through ModFlow yet, but they respect these imprecise hydraulic conductivity estimates just like we want them to. And we can see that in this plot. So this is looking across ensemble space at different locations in the model. This top plot would be a hydraulic conductivity estimate we had a lot of confidence in. So it has a narrow noise distribution. The conditional distribution is right on top of it. That's why it's like a dark color of red. So there's a red noise distribution and a blue posterior distribution, and the two of those are right on top of each other. So we've said in this model cell that's in layer 3, row 9, column 48, I wanted conductivity to be minus 0.5 in log space, and so that realization has now, the ensemble's been conditioned to respect that piece of information. The next plot is a little bit more imprecise hydraulic conductivity estimate. It has a wider distribution, also being respected. The third plot, that's one of our greater than inequalities where there was a production well. So you can see the gray ensemble has been moved to be the blue ensemble, so that the values that were already greater than that stayed in place, and we pushed the other ones to that boundary. And then on the bottom, that's our specific storage with a double inequality. We're trying to make sure all the values are in that double inequality range. Does this matter? Well, now we're going to run ModFlow for 2 ensembles. Oh, sorry, let's say one more thing. If you were in the KIP range, you would be in the gray distribution where we would just ignore these data. And if you're the Zapp-Brannigans, you would have sort of made the model cell be exactly that red line for each one of these plots. So you can see sort of the difference of what we're looking at. The blue distribution is a nice middle ground between ignoring the data and forcing the model to reproduce those data. Okay, now we're going to run ModFlow for 2 ensembles. We're going to run our uncalibrated, our original prior ensemble that's shown in gray through ModFlow. And then we're going to run our conditional ensemble. It hasn't been matched to any groundwater levels or anything else except respecting these imprecise conductivity and storage data. And we're going to look at 2 forecasts, an unseen groundwater level here and surface water groundwater exchange along those reaches during a dry time. And what we see is pretty impressive. The uncertainty reduction that we get just from assimilating these imprecise data is pretty extreme. The gray distribution, which was the true prior distribution, and the conditional realizations in blue, there's a monster reduction in predictive uncertainty just by using these really imprecise storage and conductivity estimates, right? This is, maybe we don't even need to do history matching now. Like this might be enough to just say, maybe a decision maker can make action on top of this posterior distributions without actually having to run the inverse problem. So, in closing, prior building is a largely ignored aspect of applied groundwater modeling, I think. Ensemble methods, the way that Briak and I have been doing this, provides one approach to start to do prior building and using a lot more soft knowledge in the process. No model runs are required for prior building, but common sense and critical thinking are required, like almost every aspect of what we do. And it can have a substantial impact on predictive uncertainty. If you're interested, Briak and I have put the files for the Freiberg problem I showed you today on GitHub if you want to check those out. And that is it for me.
Yeah, this is cool, especially since we don't have the same kind of regularization that we've been using in non-ensemble methods. So this is honoring the prior more. But my question is sort of with the variance bias trade-off, what you just showed. Like, what if you're way off though, right? Like the data's not, we still, it's imprecise. So you've conditioned and it's gotten better. But in that case, you didn't show the truth. And I'm curious, like we're starting to get really confident, but are we getting confident about the right place? And do we need to somehow, kind of mix the two? so that we still are looking at our residuals.
Yeah, that's right. So I alluded to that you could skip history matching just for dramatic effect, but realistically, we would never skip that. Just if for no other reason, to build consensus, right? You can say, oh, I didn't even calibrate it. Trust me, it's good. But someone's immediately going to run that and look at water levels and say, no, it's not good. So.
But it does seem to me, Jeremy, what you could do is have this as a step in your PEST chain, that you could have this and then pull it, be part of your objective function so that you're actually having it in there. But it'd be like prior information that what you give for a weight in your objective function is going to be important, but there isn't any reason you couldn't formally couple that and have that result feed into your objective function.
Yeah, that's right. So, I mean, the way I've been doing it is I run this to get the prior ensemble, but then I keep those same penalty functions available during history matching so that I can continue to monitor what's happening to those as I start to assimilate groundwater levels as well. But I like to do the stepwise process to look at those conditional realizations before you start actually doing the history matching process. I've got a couple more over here.
Is there any way for you to combine information about, say, grain size, fractions, techniques that don't tell you what the actual value of a certain property is, but it tells you that, the contrast, like you may have higher values here than there.
Yeah, so this is the thing I think we're most excited about is you can start to enforce those sort of differences in regions of the model or across layers, or that you don't know something about the pattern, but you don't know anything about the absolute values, right? That in general, this region should be higher than this region. And this is a technique to do that, right? That you could say, I want this region to be at least 20% less than this region. And if it's more, that's okay, but it needs to be at least 20% different. So you can start to use those kinds of like soft knowledge rules.
This is more commentary. I like it a lot. And instead of focusing on the absolute uncertainty and knowledge, this is putting together your story about how it's supposed to work and forcing your data set to pay attention to the story. So when you go to present it to other people later on, you don't go, oh, duh, I had no idea, or well, I couldn't figure out how to talk about it. So now you have a method to talk about it and includes that information.
That's right.
And especially when you take transmissivity or your slow recovering well, and when you ignore it all, it very much smooths over the lower T areas when you ignore that information. So it's very helpful to put this in, and at least it gives you a consistent story. So even if it's wrong, it's still a better sounding story.
That's right. Well, and for me, I mean, like everything I do, this is about shame avoidance. Like I don't want to be embarrassed later. And I had a very talented client that I work with in New Zealand who was like, we have all these K data and your fields don't look anything like these K data. I was like, oh, you have a point. Let me get back to you on that.
Do you think this method can lead to priors that are too restrictive, and how would you avoid that?
Always, and so that's that sort of common sense element, right? That you don't want to put too much confidence in these data themselves, right? That they are imprecise by themselves, but then in the context of a really coarse model versus a slug test that measured mostly the gravel pack of the well, and so that's why I like those double-sided inequalities, because that really lets you say, there's something here, but I don't have a lot of confidence in what it is. So let's gently nudge the prior in this direction without saying it needs to be really tightly respecting these estimates.
Yeah, so I like the idea a lot. It seemed really nice. And I like the idea that imprecise, there's a danger maybe being prior being too precise. But that's the only part I didn't quite understand. Are you saying you carry those constraints over when you do the data assimilation later?
That's right.
Because I would have thought that simply by conditioning your prior, that you wouldn't then need to use it again when you do data assimilation, because you would have already incorporated that information.
You do, but then what if the water levels are telling you something different? That now there's, and so maybe you want to see that conflict that, oh, now the water level's trying to bring the T back up here, even though some other estimate said it needed to be lower. So at least you can keep an eye on the potential conflict that would come up.
So it seems like you could include some information on your concept of depositional environment, geologic facies, in this type of approach. And I'm thinking about some of the totem data that we're using in California right now, whereas as opposed to AEM, SkyTem data, it's higher resolution when we're towing the instruments on the ground. And right now we're trying to square what we're seeing in the geophysics, in this big block of high-resolution geophysics data, some of it in the unsaturated zone, some of it in the saturated zone, relative to scant continuous coring that we're doing to try to figure things out. But we're developing these sort of concepts of geologic facies. It seems like you could code that in here as well. The geologist thinks that over here we've got lower energy depositional environment, and over here higher, so on and so forth.
Yep. So, and this, again, there's this place in New Zealand I'm working. They have this conceptual model with all these beautiful zones where somebody drew pictures and circles and loop-de-loops. And then somebody also went and flew SkyTim. And then we have point data. So there was a lot of potential pieces of information that were maybe conflicting in some scales and represented different support volumes. And so this was a way to try to start to incorporate SkyTim and point estimates, and also this sort of fantasy loop-de-loop things that, I mean, maybe they're not precise, but they're important for consensus building with the model, right? That somebody wants to see that, oh yeah, you at least respected that I thought there was a low zone here. And so, again, this is a method, at least I found, that it's flexible and lets you check the box that, yes, I included your knowledge and your understanding, but I'm not making the model be exactly what you said it should be.
Hey, Jeremy, I've got one. I'm over here.
Oh, Katie, hey, I knew it was you.
I'm just curious about, after just watching Marsh's presentation where he was saying, you can't just set it and forget it with a variogram. It seems like that's still what you're doing. So is there any way to kind of include that variogram squishiness into this?
I thought you might ask me this, and so I had an answer for you. So since this goes so quickly, like you're not actually running the model, you could put an outer loop around that to estimate the variogram parameters as hyperparameters, and then run IES under the hood to get to the posterior and start to look for, are the fields changing, look for the variogram parameters that give you the minimum change prior to conditional realization. So because what we want is the realizations to look most like the prior, and if we can manipulate the variogram to keep them the most like the prior while respecting the soft data, maybe that's one approach to start to try to do that. There's a